Hello everyone, here we have a very interesting question. We have a cylindrical container which is stationary and there is a very small orifice at the bottom of this cylindrical container. At the given moment, the water has the height h and the water is leaking out from that bottom orifice. We need to find the pressure at a point just inside the orifice. Got the question? I request you to please pause the video here and then post your answer in the comment box, as well as try to post the logic or the concept what you used to get the answer. Let's check the solution here on the board. So we have a cylindrical container. Suppose for this cylindrical container, we consider the area of cross section as A. The water has been filled up to the height h at this moment. So this we are taking up as h. There is a very small orifice at the bottom and the water leaks out from this orifice. Got it? Now we take few points. This is a point just inside the orifice. This point I consider just outside the orifice and another point we consider at the surface. Let's name these points. I'll call this point as 1, this as 2 and this as 3. Okay. Our target is to obtain the pressure at point 2, which is just inside the orifice. Now we can write few pressures very easily. The P1 should be how much? It should be actually equal to the atmospheric pressure. I hope you remember that whatever point is exposed to the atmosphere, its pressure is P atm, the atmospheric pressure. 1 is exposed to the atmosphere, so its pressure will be P atm, the atmospheric pressure. Same logic we can apply for 3. 3 is here, just outside the orifice, and this part is also exposed to the atmosphere. It means P3 will also be P atm. Actually, someone asks you what is the pressure here. It will be P atm. What is the pressure here? Here, whatever point is exposed to the atmosphere, its pressure will be P atm only. Now, the answer for the P2 is interestingly P atm plus rho gh. I hope you got the same answer. And if you applied the fluid statics to obtain that answer, then the logic is wrong, but the answer is correct. That's the beauty of this question. Many people apply P1 plus rho gh, if density of this liquid is rho, P1 plus rho gh to arrive at this pressure P2. But we cannot use that fluid statics along the streamlines, along the lines of flow. See here, the lines of flow will be like this, the fluid is coming out. So here the streamlines will be shown like this, the lines of flow. You understand that thing? Along the lines of flow, we can never use the fluid statics. We can use it perpendicular to the lines of flow, but along the lines of flow, we can't. So how to arrive at this answer? Actually, as we know, we have a streamline flow here. We can use the Bernoulli's equation, and for that here I am taking the gravitational potential energy to be 0. Okay. Along this streamline, we are applying the Bernoulli's equation. These 2 points, keep in mind, 1 and 2. 2 is just inside the orifice, 3 is just outside. So for point 1 and 2, using the Bernoulli's equation, P1 plus rho gh plus half rho V1 square. See, pressure here is P1. From the reference level, the height is h, so rho gh. And let's say the liquid here has the speed V1, so half rho V1 square. Now for point 2, I should write P2 plus rho g. Height is 0 from the reference level for the point 2, and here let's say the liquid has the speed v2, so half rho v2 square. Do you agree with this expression? Now, if we can relate the V1 and V2, then we can easily find the P2. I am doing that using the equation of continuity. According to the equation of continuity, we must be writing that A1 V1 should be equal to A2 V2. Actually, A1 is the area I am considering here, A2 is the area here. And since the cylindrical container is there, every cross section has the same area A. It means A1 is equal to A2. If A1 is equal to A2, it directly indicates that V1 should be equal to V2. Do you agree? And if V1 is equal to V2, interestingly, we can eliminate this term. So, P1 is PATM here plus rho GH is equal to P2, and that's the required answer. Got the concept? This answer should be obtained using the Bernoulli's equation, not the fluid statics. It's just luck by chance that you use the fluid statics P1 plus rho GH means PATM plus rho GH and you get this answer. But that logic is incorrect. Got it? Okay, let me ask you another conceptual question. Suppose I mark a point here. We call this point as 4. And at the same level, same horizontal level, this is the point 5. Can we relate the pressure of point 4 and point 5? What's your answer? Greater, less, equal? Correct. Perpendicular to the streamlines, perpendicular to the lines of flow. Lines of flow are like this, and here is the perpendicular direction. We can use the concepts of the fluid statics. Means if I consider an imaginary cylinder here, for that imaginary cylinder, the liquid is in equilibrium. So the net force should be 0. So force from here and here will balance out. It means the P4 will be equal to P5. So I hope you enjoyed the concept. Stay awesome. See you again.